Look at the device you're holding right now, or, whatever you're listening to this deep dive on. It's probably this sleek little rectangle of glass and brushed metal.
Right.
Maybe you've got wireless earbuds in. And we interact with the digital world as if it's completely weightless, don't we? We call it the cloud.
Yeah, the cloud, like it's just floating up there.
Exactly. We talk about data floating around or being beamed to our phones. It feels like magic, completely detached from the physical world. But what if I told you that to understand the bleeding edge future of artificial intelligence and programmable money, we actually have to look at 19th century telegraph operators mixing highly toxic acids in glass jars?
It is quite the pivot.
It really is.
Yeah.
Today, we're diving into a stack of documents that proves the internet isn't weightless at all. Beneath that smooth glass, there is a gritty, heavy, and sometimes deeply toxic physical reality.
It is a massive, incredibly physical scope we are looking at today, because our sources span from this really dense historical academic paper titled The Telegraphic Genesis of Bitcoin.
Such a wild title.
It really sets the tone. And we are combining that with the actual resume and e-commerce storefront of a veteran currency automation engineer named Andrew Blanford.
Right.
And we're cross-referencing all of that with a stack of his technical white papers outlining entirely new internet protocols. Things like Satoshi Gate, the Fat Cat protocol, and this global marketplace called APIs RES.
I mean, I spent the whole weekend going through this material, and it genuinely felt like finding a secret historical diary wrapped inside a sci-fi blueprint.
That's a good way to put it.
It is just amazing how these totally disparate sources like 19th century batteries, industrial rubber washers, lightning network micropayments, and DDoS protection all map onto a single cohesive vision of the future.
Yeah, they all connect.
So the mission for this deep dive is simple. By the time we are done, your understanding of what money is, what data is, and how the internet is fundamentally constructed is going to be completely rewired.
And to do that, to actually understand the future of programmable money that's outlined in these modern technical specs, we really have to start by looking backward.
Right, way backward.
About 150 years backward, actually. Because the first thing that academic paper does is hit you with a rather jarring historical correction. Electronic money is not a modern invention.
Which completely threw me. If you ask anyone on the street, we think of electronic money as, I don't know, a product of the late 20th century.
Sure, magnetic stripe cards, that sort of thing.
Exactly. We think of modern bank wire transfers and eventually things like Bitcoin. But the paper's core thesis is that Western Union's wire transfer system, all the way back in 1871, was the world's first electronic bearer token network.
And the mechanics of it are startlingly similar to modern cryptocurrency, which is what makes it so fascinating to unpack.
So how did it actually work in 1871?
Well, a sender would walk into a telegraph office and hand over physical cash. In return, the clerk wouldn't give them a receipt with a name on it. They would give them a secret password.
Like a literal password.
Yeah, a random string of words and numbers, like Granite Buffalo 73922, for example.
Yeah.
That password would then be transmitted via the telegraph network to a destination office in another city.
Okay.
Then the recipient would just walk into that destination office, present the password, and claim the funds.
I want to pause right there because the concept of a bearer token is so crucial to this whole discussion. That password literally was the private key.
Exactly.
It didn't matter what your name was. It didn't matter if you had ID.
Yeah.
Whoever held that string of characters in their hand held the money. It's like finding a $100 bill on the sidewalk. The bill belongs to the bearer, but here the bill is just information.
Right. The information was the value. And the infrastructure required to move that information across the country in 1871 is where the physical reality of this network really comes into play. You have to remember, laying copper wire was incredibly expensive.
I can imagine.
Stringing two parallel wires across the entire American frontier just to complete a standard electrical circuit would have completely bankrupted these early telegraph companies.
So what did they do?
They used something called earth return circuits. They only strung one overhead wire. And to complete the electrical circuit and allow the current to flow back to the origin, they buried massive metal plates deep in the moist soil at each station.
Wait.
They used the planet itself as the ground conductor.
When I read that, I had to read it twice. They literally used the dirt, the earth.
The literal earth. The electrical signal traveled through the overhead wire, and the return path was the Earth's natural conductivity. And the author of the paper points out a brilliant thermodynamic reality here.
Which is?
The Earth's conductivity cannot be faked. It is a strict physical constraint. You either have the physical voltage to push a signal through the dirt to the next town, or you don't.
And pushing that signal required a massive amount of power. Which brings us to a part of the paper that paints this incredibly vivid, almost, well, horrific picture of where the telegraph actually got its energy.
Oh yeah, the batteries.
Right, because there was no national power grid in the 1860s. You couldn't just plug the telegraph machine into a wall socket. So where did the electricity come from? The operators themselves had to make it by hand.
They were effectively the first network miners. Every single telegraph operator had to hand-assemble what are known as primary wet cell batteries.
And these weren't like AA batteries.
No, not at all. We were talking about clerks in back rooms mixing raw zinc, copper, and highly toxic sulfuric and nitric acids in open glass jars.
The paper specifically details these things called grove cells. These operators were working in confined spaces, mixing nitric acid, and the chemical reaction to produce the electricity would release plumes of toxic nitrogen oxide gas.
Right into the room, yeah.
Workers handled these corrosive materials with zero protective gear. Their teeth would rot, their lungs would be scarred. They were literally sacrificing their physical health, converting raw hazardous chemistry into the electrical current needed to power the carrier wave of the network.
It was brutal. Eventually, around 1860, an anonymous French inventor, known only as Monsieur Canu, introduced the gravity cell.
Which was an improvement, right?
And a massive breakthrough, yeah, because it eliminated the toxic fumes.
Yeah.
It used gravity to naturally separate a layer of copper sulfate at the bottom of the jar from a layer of zinc sulfate at the top.
Okay, so a bit safer.
It was much cleaner, but the fundamental mechanism remained identical.
Yeah.
Human labor converting physical chemistry into network energy.
Let's make sure this connection is crystal clear for everyone listening. The paper is arguing that the telegraph operator assembling a battery in 1870 is the historical equivalent of a modern ASIC Bitcoin miner.
Yes.
Now, for those who might not know, an ASIC demerit, an application-specific integrated circuit, is a highly specialized computer. Its only job is to burn electricity to solve the math puzzles that secure the Bitcoin network.
That's right.
So the paper is saying the 1870s operator and the modern ASIC miner are doing the exact same thing, converting physical resources into network security.
That is the exact parallel the author draws. And to ground this in hard physics, the academic paper introduces something called Landauer's principle.
Oh man, this part?
Yeah, this was proposed by an IBM physicist named Rolf Landauer in 1961. Landauer mathematically proved that information is physical.
I really want to dwell on this because this concept completely broke my brain. What does it actually mean that information is physical?
It means that you cannot erase or transmit a single bit of information without expending a minimum mathematically defined amount of energy. And that energy is released as heat.
So data isn't just invisible magic.
No. Imagine a bit of data as a physical switch. It's either a 1 or a 0. It's in a physical state. To change that state to erase it or flip it requires thermodynamic work. It's an unavoidable law of physics.
Wow.
Like, the heat your laptop generates when it's processing data isn't just a byproduct of inefficient fans. A tiny portion of that heat is the fundamental thermodynamic cost of erasing and altering information.
So a bit of data isn't just an abstract idea floating in the cloud. It has a physical footprint. Changing a 0 to a 1 literally generates heat in the real world.
Precisely. And this creates what the paper calls the energy data value triangle.
Unpack that for us.
Think about that gravity cell battery on the telegraph operator's desk. The battery doesn't just store abstract energy. The physical chemical gradient inside that jar, the separation of the copper and zinc sulfates, stores information about work that can be done.
Okay, I'm tracking.
So the physical grounding of the telegraph, using the Earth's unfakeable conductivity, is perfectly analogous to the thermodynamic grounding of Bitcoin.
Right, because Bitcoin uses proof of work.
Exactly.
Yeah.
Neither can be spoofed. You cannot fake a chemical reaction, and you cannot fake the electricity required to mine a Bitcoin block. Both require the expenditure of real-world energy to validate the information.
And the paper even talks about these 1860s shed tinkerers. These were everyday people buying glass.
Early hobbyists.
They were learning how to inject signals into this continuous electrical carrier wave. And the author compares them directly to early Bitcoin adopters in 2009 and 2010.
The comparison is very apt. Early Bitcoiners were running Node software on their laptops, learning how to format transactions, and inject them into the mempool.
Let's define the mempool real quick for our listeners who might not be deep into crypto.
Of course. The mempool, which is short for memory pool, is essentially a digital waiting room.
Okay.
When you send a Bitcoin transaction, it doesn't instantly go onto the blockchain. It goes into the mempool, waiting for a miner to pick it up, verify it, and permanently record it in a block.
Got it.
So, just as 19th century tinkerers were learning to format Morse code pulses to ride the electrical waves of the telegraph, early computer geeks were learning how to format digital signatures to ride the cryptographic wave of the mempool. They were mastering the base protocol of their respective eras.
Which sets up this massive tragic irony. If the 1871 telegraph was the world's first electronic bearer token, and it was built on a thermodynamic carrier wave by this decentralized army of backyard tinkerers, what went wrong?
Yeah, the big question.
Why didn't we get a decentralized financial utopia in the 1880s? Why did we end up with massive monopolistic corporations controlling all global communication?
That is the million-dollar question. And it brings us to a phenomenon the author calls the monopoly virus and the very real mechanics of network capture.
Okay, let's get into this.
The paper outlines a specific sequence of structural events that happened during the U.S. Civil War. And I should note, the author frames this strictly through the lens of network mechanics.
Right, we're not taking political sides here.
No. Whether you view these historical events as necessary wartime emergency measures or as opportunistic corporate power grabs, the actual mechanism of how the infrastructure was captured is what's important here.
Right, we're just looking at the plumbing of how a decentralized network gets swallowed whole.
Exactly. The author describes a 5-step capture playbook executed between 1861 and 1866. Step 1 is a crisis creates an emergency.
The Civil War.
Right. In 1862, Abraham Lincoln effectively seized the commercial telegraph lines for the war effort. Suddenly, the decentralized nodes are under central command.
Okay, that's step 1.
Step 2, corporate executives embed in government. Anson Stager, who was a top executive at the private company Western Union, was simultaneously put in charge of the military's telegraph operations.
So the guy running the private monopoly is now wearing a military uniform and running the government's network. The conflict of interest is staggering.
It really is. And step 3 naturally follows. A censorship apparatus is built on top of the physical infrastructure. Because it's a military operation, they control exactly what information can flow, who can send it, and who is blocked.
Makes sense during a war, but then the war ends.
Which brings us to step 4. The physical infrastructure, much of which was aggressively expanded using government resources and taxpayer money during the war, is handed back over to private control.
Let me guess. To Western Union.
Specifically to the companies whose executives were running the military operations, yes.
Which leads to step 5, the final lock-in, the natural monopoly defense.
Right.
Western Union successfully argued to the public and lawmakers that having 50 different telegraph wires strung up on a street from 50 different companies was inefficient and chaotic. They argued that communication was a natural monopoly and they were the only ones equipped to manage it.
And the end result of this 5-step process was absolute capture. Before the war, Western Union was just one of over 500 decentralized competing telegraph companies.
500.
Yeah. But by 1866, they controlled over 90% of the entire U.S. market. They'd captured the physical layer, which meant they controlled the information layer, and ultimately the financial layer.
And the paper takes the specific Civil War example and expands it into this massive macro theory called the 150-year grounding cycle. The author tracks how humanity makes these massive technological leaps that ground physical potential into useful forms.
And how those leaps are inevitably followed by a war for control.
Exactly. It's a fascinating timeline. The paper starts with Isaac Newton's scientific method in 1687, grounding the laws of physics. Then James Watt's steam engine in 1769, grounding thermal energy. Morse's telegraph in 1838, grounding electrical information.
Tesla's AC power in 1888, grounding the electrical grid.
The internet in 1969, grounding digital information. And finally, Bitcoin in 2009, grounding digital value.
What's terrifying is that if you look at the gaps between these breakthroughs, the timeline is compressing.
It's speeding up.
Considerably. It goes from 247 years between Newton and steam down to 82 years, then 69, 50, 81, and finally just a 40-year gap between the creation of the internet and the creation of Bitcoin.
And with each of these compressing cycles, the battles for control, what the author calls the protocol wars, become more intense. The most famous example is the battle over the electrical grid. Edison's direct current versus Tesla's alternating current.
Ah, yes, the war of the currents.
Edison was the massive incumbent. He had all the money and power, and he was using incredibly dirty tactics to protect his DC monopoly. He was publicly electrocuting animals to convince people that Tesla's AC power was dangerously unstable.
But Tesla's AC protocol was simply superior physics. DC power could only travel short distances before losing its strength, meaning you needed a power plant in every neighborhood.
Not very efficient.
No. AC power could be stepped up to high voltages, transmitted over vast distances, and stepped back down safely. It was mathematically and physically superior, and it ultimately won. However, Tesla's subsequent attempts to innovate were not so lucky.
This is where we get into the Wardenclyffe Tower incident, right?
Yes.
In 1901, Tesla convinced J.P. Morgan to fund this massive futuristic tower in New York. Morgan thought it was for wireless telegraphy to compete with Marconi. But Tesla secretly wanted to use the tower to transmit wireless power. He wanted to use the Earth's resonance to provide free energy to the entire globe.
And what happened when J.P. Morgan realized the true purpose of the tower? The famous quote attributed to the situation is that Morgan asked, "Where do I put the meter?"
Wow.
If you can't meter the energy, you can't charge for it. You can't control it. So Morgan pulled the funding immediately, and the tower was eventually demolished and sold for scrap.
That's heartbreaking.
The paper also includes a very interesting historical footnote. When Tesla died in 1943, the U.S. government immediately invoked the Alien Property Custodian Act and seized all of his research papers from his hotel room.
And who did the government call in to evaluate these potentially world-changing free energy documents? John G. Trump, an MIT professor and the uncle of Donald Trump.
Exactly. Trump evaluated the papers and concluded they were mostly speculative and philosophical, posing no military threat.
But regardless of what was actually in the papers, the structural pattern is the crucial takeaway. The moment decentralized technological potential threatens centralized economic control, the centralized authority moves to seize the raw data.
The author distills this entire cycle down to what they call the perpetual paradox. It goes like this. Data creates potential. That potential generates wealth, which attracts forces of control.
Right.
Control requires gathering even more data to maintain the monopoly. But fundamentally, data naturally resists control because entropy always increases. Information wants to spread.
Which brings us back to why the 1871 Telegraph failed as a decentralized bearer token. The cryptography wasn't the problem. The flaw was that the final proof of work relied on trusting a human clerk.
Yes, the human element.
A clerk could be bribed, a clerk could be extorted, the government could walk in and order the clerk to freeze the transaction. As long as a human is required to validate the state of the network is capturable.
And the academic paper argues that Bitcoin fundamentally solves this human flaw. And it solves it through a concept the author calls lost sats.
Let's explain what a sat is.
A sat, or Satoshi, is the smallest unit of a Bitcoin. Millions of Bitcoin have been permanently lost over the years. People threw away their hard drives or forgot their passwords.
We've all heard those stories.
Right. The paper argues that these lost coins aren't a failure of the system. They are actually what gives the system its ultimate thermodynamic grounding.
It's a profound way to look at network stability. The author describes lost Bitcoin as data that has attacked itself into permanence.
That's a great phrase.
Because the private keys are gone, those coins can never, ever be moved. Yet the entire network continually expends energy to maintain the ledger that proves those coins exist in their frozen state.
They act as a permanent thermodynamic ground reference. They are mathematical proof of past energy expenditure that no human, no government, and no monopoly can ever alter or seize.
Okay, I have to jump in and heavily push back here.
Go for it.
The author is painting this very elegant picture of Bitcoin solving the 150-year capture cycle. But if the cycle is constantly accelerating and Western Union captured the telegraph and J.P. Morgan captured the energy grid, what is actually stopping Bitcoin from being captured by the exact same monopoly virus?
It's a fair question.
The academic paper itself points out modern vulnerabilities. It mentions things like op-return bloat. Can we break down what that means? Because it sounds like we were walking right back into a trap.
It is a very real threat, and you are right to push back. To understand op-return bloat, we have to look at the mechanics of the blockchain.
Okay.
The op-return function in Bitcoin was originally designed to allow users to attach a tiny, tiny snippet of arbitrary data to a financial transaction, maybe a short memo or a receipt number.
Just a few bytes of text.
Exactly. But recently, people have figured out how to use this function to shove massive amounts of non-financial data onto the blockchain. They're inscribing high-resolution images, JPEGs, audio files, and even video games directly into the ledger.
Which means every single person running a Bitcoin node on their home computer is suddenly forced to download and store all of these random JPEGs forever.
Exactly. And this leads to the bloat. If the blockchain grows too massive too quickly, the hard drive space and the computing power required to run a node become prohibitively expensive for a normal person.
So the little guy gets priced out.
Yes. If the average person in their living room can no longer afford to run a node, who is left validating the network? Only massive data centers, giant corporations, and institutions like Amazon Web Services.
And boom, we are right back in 1866. The network is centralized in the hands of a few giant monopolies who can dictate the rules, censor transactions, and capture the system. If it costs $10,000 a month in server fees to run a node, the decentralized dream is dead.
Which is the perfect transition to the remaining sources in our stack. Because the only way to prevent this kind of network capture is to secure the physical layer.
You can't just code your way out of it.
No, you cannot just write clever software and hope for the best. Software exists in a theoretical vacuum. To protect the network, you have to enforce the rules in the physical world, where friction, heat, and entropy actually exist. And that is exactly the puzzle Andrew Blandford was trying to solve.
I found Blandford's background so fascinating because it defies every expectation.
Oh, absolutely.
If you tell me we are looking at the creator of edge-native smart contracts who is trying to save decentralized money from corporate capture, I instantly picture a 22-year-old Silicon Valley crypto bro in a hoodie drinking Soylent.
That's the stereotype.
But then you look at Andrew Blandford's resume, and he is a hardcore industrial pragmatist. It's like finding out the lead architect of The Matrix is actually a master plumber from Ohio.
His background is the antithesis of the typical Silicon Valley software developer, and that is precisely why his protocols are designed the way they are. For over a decade, Blandford was a senior field engineer at Giesecke and Devrient, often referred to as G&D.
Ah.
His specific expertise was maintaining the BPS 3000 high-speed currency inspection systems.
Now, we looked up the BPS 3000. These are not little counting machines you see at a local bank branch. These are massive, room-sized industrial machines. Blandford was working on these at the Federal Reserve Bank of Denver and the Federal Reserve Bank of New York.
Yes, these machines process millions of physical fiat banknotes an hour. They are sorting, inspecting for counterfeits, checking for degradation, and destroying old bills.
So he knows physical money.
Very well. Blandford was the guy with his hands inside these massive mechanical beasts. He was dealing with the physical reality of money. Paper dust, jammed gears, torn bills, friction, heat. Before that, his resume shows him maintaining centralized Xerox laser printing systems and IBM mainframes. He spent his entire career in the trenches with heavy, failing hardware.
Which completely explains his current venture. Because he doesn't run a software startup. He runs a company called Primal 23 Industrial.
Yeah.
We spent a lot of time looking at their e-commerce site, and they manufacture and distribute industrial rubber washers, spacers, and gaskets.
It seems like a complete non sequitur at first glance. What does a protocol developer have to do with rubber washers? But if you look at their product catalog, specifically the Endeavor series and the Performance series, you start to see the philosophy.
I want to dwell on the materials they sell, because this is where the thermodynamic grounding really clicked for me.
Sure, go ahead.
They sell neoprene washers, which are general purpose but handle temperatures up to 250 degrees Fahrenheit. They sell EPDM rubber, specifically formulated for harsh indoor and outdoor weather resistance.
Right.
They have silicone washers that are food grade and can withstand 400 degrees. And then they have fluorosilicone, which is highly resistant to corrosive fuels and oils and can survive up to 450 degrees.
So why does a man who thinks deeply about the architecture of global financial networks sell abrasion-resistant rubber? Because it represents a foundational understanding of physical constraints.
Exactly.
Pure software developers often write code based on frictionless assumptions. They assume zero network latency, infinite server uptime, perfect data integrity, and a completely sterile environment.
But the real world isn't like that.
No, Blandford knows that the real world is chaotic. It is hot, it is corrosive, machines break, connections drop, and parts grind against each other. A washer exists entirely to mitigate friction and environmental degradation between two moving parts.
He understands physical grounding because he has spent his life fixing the things that break when software meets reality. And he takes this deeply mechanical industrial mindset and applies it directly to the digital architecture of Bitcoin.
It's a unique perspective.
He looks at the monopoly virus and says, You don't fight this with airy-fairy, highly complex code that can easily be manipulated. You fight this with highly constrained physical, hardware-enforced logic.
Which brings us directly to the technical white papers for his creations, the Satoshi Gate Protocol and the Fat Cat Protocol.
Let's start with Satoshi Gate. When I first read this, I assumed gate meant like a toll booth, but it actually refers to logic gates.
Like in computer engineering.
Right. Blanford designed 13 composable payment primitives, but he didn't design them like modern, flexible software functions. He designed them to act exactly like rigid electronic hardware circuits.
Right, he is mapping financial transactions onto the fundamental building blocks of computer chips. For instance, the most basic primitive is the SAT gate. It acts as a simple buffer. You pay a specified number of satoshis, and the gate opens, granting you access to a piece of data.
Then he introduces combinational logic. There is the SAT and DIG gate. This acts as a multi-condition escrow.
Give us an example.
Imagine a business deal where payment A from the buyer and payment B from the broker must both arrive before the digital asset is unlocked. If only one arrives, the gate stays closed.
He also built an SAT OR gate for flexible payment routing. Perhaps a user can access the service by proving they hold a monthly subscription token, or they can pay a one-time microfee per use. The gate accepts either valid state.
Oh, that's smart.
And the SAT XOR gate exclusive OR is crucial for preventing double billing, ensuring that only one payment method is accepted for a mutually exclusive choice.
And he didn't stop at combinational logic. He incorporated sequential logic. This is where my mind was blown. The SAT flip-flop.
Yeah, this is a big one.
In actual electronics, a flip-flop circuit is used to store a single bit of state memory. It remembers if a switch is on or off. In the Satoshi Gate protocol, a SAT flip-flop acts as decentralized payment memory.
I want to emphasize how revolutionary this is for network architecture. Normally, if a website needs to remember if you are a paying subscriber, they have to maintain a massive centralized database with your username, password, and credit card status.
Which is a huge target for hackers.
Right. But a SAT flip-flop eliminates the database entirely. The state, whether you are subscribed or unsubscribed, is determined dynamically based purely on the sequence of cryptographic payment proofs provided by your wallet. The network holds the state without needing a central server to remember you.
He even built routing logic into these primitives. The SAT-MUX acts as a multiplexer, routing payments based on the type of content being requested. And the SAT-MUX does the opposite. It can take a single incoming payment and automatically split the revenue between multiple parties in sub-second time.
Incredible.
And the craziest part is the hardware he expects this to run on. It's called the Fat Cat protocol, or BTC-TKP.
BTC-TKP stands for Bitcoin Telephone Keypad Protocol. Blanford essentially mapped complex Bitcoin cryptographic operations onto a standard retro 12-button telephone keypad, digits 0 through 9, the star key, and the pound key.
When I first read that, I laughed. It sounds almost absurdly primitive. Why on earth would you map the future of programmable money to a 1980s telephone keypad?
Because of what he calls edge-native offline smart contracts. He is optimizing for absolute physical resilience. The white paper details how these protocols run on an ATC 608A secure element.
That's a tiny chip, right?
Yes, a tiny, incredibly robust cryptographic chip. He pairs it with a basic ESP32 microcontroller. The total cost of the hardware is roughly $15 to $20.
Okay, I need to stop you here because I was struggling to visualize this when I read the white paper. The paper gives an example of an offline vending machine using this $15 setup. It claims the machine can operate in the middle of a forest for weeks without any internet connection.
That's the claim.
If the machine has no Wi-Fi, no cellular data, and no connection to the Bitcoin blockchain, how does it know my payment actually cleared? How do we prevent someone from double spending in the woods?
It is a brilliant use of hardware cryptography. The machine itself doesn't need to check the global blockchain in real time. When you interact with the machine, your phone, which does have a connection, fetches the necessary data.
Oh, I see.
You beam your cryptographic payment proof to the vending machine via a local interface like Bluetooth or NFC. The ATA's 608A secure element inside the machine acts as a physical vault. It cryptographically verifies that your payment signature is valid and mathematically sound.
Without needing the internet.
Exactly. If the math checks out, the secure element physically signs a state transition. It dispenses the soda, and it securely logs the transaction internally.
So the machine validates the math locally, and then later, when the vending machine owner comes by with a tablet to restock it, they download all those cryptographically signed state transitions and broadcast them to the main blockchain to actually settle the funds.
Exactly. The local validation takes roughly 116 milliseconds. It is hardware-enforced logic operating at the extreme physical edge of the network.
Blanford describes this entire philosophy as the blue-handled screwdriver, and he directly contrasts his Satoshi Gate primitives with the biggest smart contract network in the world, Ethereum.
This is a crucial distinction. Ethereum was designed to be Turing-complete. Turing-completeness means a programming language can theoretically compute anything, given enough time and memory. It allows for arbitrary loops, complex recursive calls, and highly expressive software.
It's essentially a massive global Swiss Army knife. You can build anything with it. But the downside of a Swiss Army knife is that if you aren't careful, you can accidentally stab yourself in the hand.
And in computer science, this stabbing yourself manifests as the halting problem. Because Ethereum allows for infinite loops, you can never mathematically prove ahead of time if a complex script will finish running or if it will get stuck in an endless loop forever.
This is exactly why Ethereum has such unpredictable and sometimes astronomically high gas fees, right?
Right.
Because the network has to charge you for every single step of computation just in case your code runs forever and crashes the system.
Yes. And more importantly, it is the root cause of massive catastrophic exploits.
Right.
Take the infamous DAO hack in 2016.
Right, I remember that.
Because Ethereum is Turing-complete, a hacker found a vulnerability that allowed a smart contract to recursively call itself, basically asking for a withdrawal over and over again before the system could update its balance. $60 million vanished in hours because the code was too complex to fully audit.
And Blanford looked at that and said, this is no way to build a global financial system. So he made Satoshi Gate intentionally not Turing complete. It has no arbitrary loops. It has no recursion.
The stack depth is entirely predictable. Blanford argues that for money, this limitation is a massive feature, not a bug.
Less is more.
Exactly.
Right.
By eliminating loops, you eliminate the halting problem. Because the execution path is predictable, you can batch operations, leading to a 10,000x reduction in computing costs.
That's insane.
Furthermore, it almost entirely eliminates the attack surface. A hacker can't trick a SATN gate into an infinite loop. The hardware simply won't process it. A tool optimized perfectly for one specific job, like a sturdy blue-handled screwdriver, is vastly superior and safer for critical infrastructure than a universal tool that can fail in unpredictable ways.
I follow the logic, but here's my major question. If Satoshi Gate is just a simple screwdriver and you can't run complex software loops, how does this actually power the dynamic, complex internet of the future? How do you build an economy with just a few basic gates?
That is where we move beyond digital logic and look at the analog components Blanford designed. Because these analog primitives are what he uses to completely invert the economics of modern internet infrastructure.
These analog components absolutely blew my mind. Let's walk through the mechanics of them. He starts with the SAT diode. Now, in physical electronics, a diode is a component that only lets electrical current flow in one direction.
Right.
In Satoshi Gate, a SAT diode creates a one-way, mathematically irreversible payment flow.
This is incredibly useful for things like decentralized crowdfunding. Once a specific funding threshold is met, the SAT diode locks the funds and forces them to flow forward to the creator. They cannot be redirected or pulled back.
Then you have the SAT transistor. A physical transistor uses a very small electrical current to control a much larger current. In Blanford's protocol, the SAT transistor acts as liquidity control.
A user can make a tiny collateral payment that mathematically authorizes the movement of vastly larger funds. The white paper highlights this as a perfect mechanism for Lightning Network watchtowers, where a small fee ensures a third party monitors your channels for fraud.
Next is the SAT capacitor. In a circuit board, a capacitor stores up electrical energy and discharges it in bursts. The SAT capacitor acts as a financial buffer. It can absorb hundreds of tiny off-chain micropayments, hold them securely, and then discharge them as one single batched on-chain transaction.
Which saves massive amounts of money on network transaction fees.
But out of all of these, the absolute most impactful component, the one that could fundamentally change how the web operates today, is the SAT resistor.
The SAT resistor is brilliant because it introduces programmable economic friction, and its primary use case is solving one of the most expensive and pervasive problems on the internet today: distributed denial of service, or DDoS, attacks.
Let's contextualize this for the listener. Right now, If a malicious actor controls a botnet of 1 million infected computers and they decide to attack your small business website, they just flood your server with millions of fake requests until your server catches on fire and crashes.
It happens all the time.
How do you defend against that today?
Currently, your options are terrible and expensive. You can try IP blocking, but that's a game of whack-a-mole, and you often end up blocking legitimate customers by mistake.
Right.
You can throw up CAPTCHAs, those annoying puzzles asking you to identify traffic lights, but they ruin the user experience, and modern AI can easily solve them anyway. Or, your final option is to pay thousands of dollars a month for a massive enterprise cloud protection service like Cloudflare to stand in front of your server and absorb the hit.
Which means traditional DDoS protection costs the victim money. You are penalized for being attacked. Blandford's SAT resistor completely inverts this economic reality. Instead of paying for a massive firewall, you simply route your server traffic through a SAT resistor, and you set a microscopic base price for access.
Say, 1 Satoshi per API request.
1 Satoshi is currently worth about 6/100ths of a penny.
Right. So for a normal user browsing your site, clicking a few links, the cost is literally pennies. It's invisible friction. It doesn't deter human behavior at all.
But consider the math for the attacker. If a botnet tries to slam your server with a 1 million request attack, the server simply replies with a cryptographic invoice for each request. To execute the attack, the hacker suddenly gets hit with a $600 bill. If they try a billion request attack, they go bankrupt.
The attacker is forced to fund the infrastructure they're trying to destroy. It's genius. The white paper distills this into a core philosophy. Don't gate pages, gate data.
What does that mean practically?
You let the HTML and the CSS of your website load completely for free. That way Google can still index your site for SEO, and humans can read the landing page. But the moment a user clicks a button that hits your database, the heavy, expensive computing work, it hits the SAT resistor.
It is an elegant application of thermodynamics to network security. You are forcing the requester to prove they have expended real-world energy represented by the Satoshi before you allow them to consume your server's energy.
It's beautiful.
But a practical question arises. How does a human user actually pay 1 Satoshi continuously without having to click approve transaction on their phone 100 times a minute?
And this is where the puzzle pieces snap together, because we introduced the L402 protocol. L402 is an evolution of a standard HTTP error code. We all know HTTP 404 means page not found, but HTTP 402 is an official standard that means payment required.
Okay.
The L402 protocol integrates that HTTP standard directly with the Lightning Network.
And this protocol is not really designed for humans. It is designed for the impending wave of artificial intelligence. L402 allows AI agents to navigate this microtransaction economy completely autonomously.
Right.
Walk us through what that actually looks like in practice, because the idea of an AI having its own wallet is wild.
Imagine you instruct an AI agent to compile a comprehensive market research report on global supply chains. The agent browses the web, finds a highly specialized database, and attempts to pull the data. But the database is protected by a SAT resistor.
So the agent hits a paywall.
Yes, the old internet, the agent would just fail, because a human would need to pull out a plastic credit card and type in the numbers.
But with L402, the machine handles it.
Exactly. The AI agent detects the HTTP 402 error. It reads the Lightning invoice mathematically embedded in that error response. It quickly evaluates the Satoshi gate logic.
Like deciding if it's worth the price.
Right. Maybe it's a SAT-XR gate offering a choice between a bulk data discount or a per-query fee. The AI evaluates the most efficient path, pays the invoice instantly using its own pre-funded Lightning wallet, the SAT gate opens, and the agent retrieves the data. All of this happens in sub-second time with zero human intervention.
It is machine-to-machine commerce operating at the speed of light. It fundamentally changes the internet from an advertising-based model to a utility-based model.
It really does.
But naturally, when I read all this theory, I was skeptical. Is this just theoretical white paper fantasy? But then we got to the final source in the stack, and it proves that Blandford's hardware resilience and this economic inversion are already operating in the wild.
The final piece of the puzzle is the live marketplace called API Arias. It functions as a Bitcoin Lightning-gated API marketplace.
Catchy name.
It is. And it is taking this exact technology and applying it globally, directly solving the problem of financial exclusion that was first created by those telegraph monopolies back in 1871.
The metrics on API's Arias are staggering. They currently have 147 independent suppliers globally, earning passive income from raw data. These suppliers are averaging $800 per sensor per month. The platform paid out over 500,000 sats last month alone.
That's real economic activity.
And the specific real-world examples from their catalog illustrate the profound human impact of this technology.
Consider the Nigerian fishing co-op mentioned in the text. They've installed cheap, $300 wave and tide sensors on their local fishing vessels. These sensors gather incredibly valuable, real-time oceanographic data.
But normally they couldn't sell that.
Exactly. Under the traditional financial system, these fishermen had absolutely no way to monetize this data because they lack access to Western banking infrastructure, merchant accounts, or Stripe integration.
But through APIs are us, they don't need a bank. They simply list their sensors API. There is no KYC. Know your customer friction. Ocean researchers at universities worldwide hit that API and automatically pay 8 sats per call via the Lightning Network.
Another powerful example is the Vietnam Agricultural Station. A team of researchers had deployed a $2,500 soil moisture and temperature sensor array deep in the Mekong Delta. But their institutional grant money ran out.
Which usually means the end of the project.
Under normal circumstances, that equipment would be powered down and abandoned to rust in the mud. Instead, they plugged the array into the API's RUS marketplace.
And the result was immediate. Global agricultural corporations, who desperately need live soil data from the Mekong Delta for commodities trading, now pay 15 sats per query to access that live feed.
It's a lifeline.
The sensors generate about $1,200 a year. The array is totally self-sustaining. It pays for its own maintenance and internet connection, keeping critical climate data flowing long after the traditional fiat grant died.
We see the same pattern with the Congo Weather Network, which is proxying vast amounts of localized African climate data to Western universities. And the business model of API's ROS that facilitates all this is brilliant in its simplicity. They operate on a strict wholesale versus retail model.
Break down how that wholesale model actually works.
The data provider, whether it's the Nigerian fisherman or the Vietnamese farmer, sets their own wholesale price per query based on their local costs. API's RUS guarantees that price.
Okay, so the farmer gets their cut.
Yes. When an end user queries the data, API's RS buys the data wholesale via the Lightning Network instantly, and then handles all the retail marketing, API key management, and enterprise billing on the front end. They abstract the complexity away from the sensor operator.
So you have a researcher at Stanford buying data from a sensor in the Mekong Delta that was literally dead in the water a month ago. By plugging into this 12-button, hardware-grounded Lightning Network, they made the physical sensors pay for their own upkeep.
It's remarkable.
It's like turning every idle thermometer, security camera, and weather station on the planet into an autonomous, self-sustaining micro-business.
And if we connect this incredible modern reality back to the historical academic paper we started with, the author actually has a term for this. They call it meta-Bitcoin. It's the concept of cash-to-cash state transmission.
What does that mean physically, cash-to-cash?
Think about what is physically happening when that Stanford researcher queries the Vietnam sensor. It isn't just a financial transaction. A physical SAT capacitor chip on the farm in Vietnam is transmitting a quantum of data state directly to a SAT capacitor at Stanford.
Okay, I follow.
And it is utilizing the massive global energy of the Bitcoin blockchain as a perpetual, unfakeable carrier wave to secure that transmission.
It's using the energy of the miners to validate the reality of the soil moisture.
Exactly. And because it utilizes this permissionless carrier wave, it creates a massive socioeconomic breakthrough. The API's RUS documentation refers to this as freeing trillions in locked data.
That's a huge claim.
But it's true. By removing the need for KYC compliance, bypassing the entrenched legacy banking monopolies, and eliminating the friction of monthly subscription models, a physical sensor located absolutely anywhere on Earth can immediately participate in the global economy.
It resolves the exact capture problem we saw with Western Union in 1866. Western Union required you to use their clerks, their ledgers, and their physical copper wires. You needed their explicit permission to participate in the network, and they could revoke it at any time.
But this changes the paradigm.
By shifting the ground of the network from physical telegraph wires controlled by a corporate board to a thermodynamic proof of work secured purely by math and physics, the network becomes truly permissionless.
It is an incredible historical and technological journey when you lay all the pieces out sequentially.
It really is. I mean, just look at the arc we've covered today in this deep dive. We started in the 1860s looking at ordinary workers sacrificing their health, handling toxic nitric acid to build the wet cell batteries that provided the raw thermodynamic energy for the world's first monopolized bearer tokens.
A dark start.
We move through a 150-year history of protocol wars, watching network after network get captured by corporate monopolies the moment a human intermediary was required.
Then we met Andrew Blanford, an industrial engineer who spent his life up to his elbows in the physical machines that count our fiat currency, and manufacturing the heat-resistant rubber washers that keep the real world from grinding to a halt.
And we saw how he took that deeply pragmatic physical understanding of friction and entropy and applied it to digital protocols. Using retro 12-button keypads, $15 secure microcontrollers, and logic gates that perfectly mimic physical electronic circuits, he built a system that completely inverts the economics of cybersecurity.
Truly groundbreaking.
He turned DDoS attacks into revenue streams, and in the process, unlocked a global machine-to-machine data market.
It serves as a profound reminder that the digital world you interact with every single day, the emails you send, the websites you browse, the AI prompts you write, is completely bound by physical laws. Information is physical.
And someone has to control that layer.
Right. And the architecture being built right now by pragmatists like Andrew Blanford is determining who will control that physical layer for the next century. Will it be captured by corporate monopolies again, or will it be a permissionless, mathematically enforced microeconomy?
Which leaves us with a final, slightly haunting thought for you to mull over as you go about your day. Let's go back to Landauer's principle. If that principle is absolute truth, if information is truly physical and cannot be created or erased without generating a thermodynamic cost, then every search query you type, every photo you like on social media, and every digital action you take generates a tiny, undeniable physical footprint.
Heat is released. Work is done.
Now, as AI agents begin transacting autonomously across these ASIC-gated networks, using this physical energy as currency to buy and sell data at the speed of light, it raises a question. Are we, the human users, generating the original data and the original prompts, becoming the new telegraph battery operators? Are we just generating the raw carrier wave energy for a machine economy that no longer needs us to pull the switches? Because at the end of the day, that smooth, weightless glass screen you're holding in your hand, well, it still has a physical weight.